So for the first part, we will look at question 1A, and after that, we're also going to look at question 1B. We'll look at this one and we'll look at this one. So these expressions are quite interesting. They both involve the use of an algebraic substitution. So let's start with the first one there. The first one, we have e to the power root of x plus 1. And then here you have root of x plus 1. So this is kind of a special case, and you kind of have to try, because if you think about any other technique that you might want to use here, what you notice is that they are all going to probably be tricky to evaluate. So instead, let's try U substitution. So for U substitution here, it's tricky how it works really. It's tricky to see, but after you make the substitution, in the end, some things must cancel out. The new variable should be the only thing that remains. So to work out this, we will let U be equal to the power of the exponentials. The exponential there is the complicated part. So let U be equal to the power of the exponential, which is root x plus 1. So of course, this implies that U is just equals to x plus 1 to the power half there. Then from here, we can obtain the derivative du dx. When you differentiate this, the power comes down, and then the argument remains the same, x plus 1. And then the power reduces by 1, it becomes negative half. So of course, when we rewrite this, it's now du dx by laws of indices. This becomes 1 over 2. Then this part with the negative power can now be written as 1 over x plus 1 to the power positive half. So of course, when this term goes down, the power there becomes positive. So that now we can present it as half and then 1 over root of x plus 1, when the half there goes back to being a root. So I've basically reversed what I did when I wrote it as power half from a root. So we're seeing that here, du dx is just equal to 1 over 2 root x plus 1. So our goal here is to find what dx is. So from here, of course, when we cross multiply, we have 2 root x plus 1. And then we have du being equal to dx. So we now have an expression for dx. So when you go back to our integral, it was the exponent of root x plus 1. Remember, we said root x plus 1 was u, so it's just e to the u here over the denominator was, I can keep the denominator as u. Remember, u again is root x plus 1. So if you look at this, the denominator is root x plus 1. So you might as well put u there as well. It won't matter whether we keep it like that or put u. Multiplying dx. So in place of dx, we have 2 root x plus 1. And then du. Now, here, of course, you have to notice that this root x plus 1 again, remember we're saying u is root x plus 1. So you might as well put u there as well. So this is 2u du. Now this u here gets to cancel with this one here because they are the same. Even if you had kept the u that was in the denominator here as root x plus 1, you'd have seen that it would have cancelled right at this stage in this case. But you can take that approach or you can cancel it from here. We have a question? So with the u gone, notice that the integral now reduces to something simpler. It's now the integral of 2 e to the u du, which is 2 the integral of e to the u du. The 2 is a constant, so it can come out of the integral. Now remember, the derivative of e to the x with respect to x is equals to the same e to the x. This implies that the integral of e to the x with respect to x is the same as e to the x. So in our current case, we have the integral of e to the u with respect to u. This will remain the same, e to the u. But because we had no limits of integration, we'll say plus c there. So that becomes our integral. But remember, the variable here must go back to the original thing. So you have to bring back what u is. Initially, we said u was what? It was expression. We do recall that we said u was what when we started this? U was equal to the root of x plus 1, meaning this is going to be 2e to the root of x plus 1 and then plus c. So this is going to be the final solution to this expression.